Today we're going to be finishing section 9.3, which is applications and probability. You guys actually watched a video over the first application that it talks about in this section, which is odds. The other application in this section that it references is something called expected value. If the possible outcomes for an experiment are A1, A2, all the way to AN, and these have to be numerical outcomes, by the way, for this to work. So think of things like rolling a die, right? Numbers come up. With probabilities P1, P2 to Pn, then the expected value is the outcome A1 times its probability P1, plus the outcome A2 times its probability P2, until we get to A sub n, P sub n. And a fair game is a game where the expected value is 0. So when we're thinking about these kinds of problems, we're thinking about games like casino games, games like raffles, games like lotteries. Stuff like that is the kinds of things that you can talk about an expected value. So you can look at, what would be the expectation if you went and you bought a lotto ticket on your $5 investment in that ticket. What can you expect over time if you continue to do this multiple times? Obviously, fair games are not the norm. If the game were fair, the casino couldn't build the beautiful building. They couldn't pay their workers. Like, seriously, right? It happens the same way when you think about like carnival guessing games. Right? The carnival's got to make money. That's the whole point. So the game can't be actually fair. But you can have games where you're more likely to win than others too. And expected value can help determine that outcome. So we're going to look at a game that you may or may not be very familiar with. And to be honest, I'm not super familiar with it, but I know enough to be able to talk about it from a surface point of view. So have you seen a roulette wheel before? Okay, so roulette wheel looks like a spinner. The spinner has different colors on the different slices of the pie. It has different numbers on the different slices of the pie. There's lots of ways you can place bets on a roulette wheel. You can place bets on specific numbers. You can place bets on specific colors. You can place bets on evens or odds. Or you can place bets on multiple numbers. Like you can say, well, I'm going to put my money on it either showing up as a 1 or a 7. Like, so you can do multiple numbers. So on the roulette wheel specifically, there are slots that are numbered 00 through 36. So how many slots are there? 38, because you got 00 and you've got 0. Yeah, it's weird. So there's 38 different little slices on there. One way to bet is to bet on a single number. If the ball lands on your number, you receive 35 chips plus the chip you played. So that's a big time payout, right? If you bet $1, it would pay you $35 back. You get with me? But again, you have a 1 in 38 chance of that happening. So the probability is low, but the payout's high. So the first thing that we're going to examine is what is the probability that you will land on 00. So how likely is it that we land on 00? 1 out of 38. And how likely is it that we land on just 0? 1 out of 38. So we could very easily also conclude then what is the probability? This is not quite asked this way, but we will be asked this in a moment. What is the probability that lands on 0 or 00? 2 out of 38. And if you wish, you could reduce that to 1 out of 19. But we're going to leave it as 2 out of 38. It'll be easier for us in a moment. Okay. So the next scenario is like a true story. My father-in-law, who is a super lucky guy, by the way. So none of these probabilities even make sense when you're talking about him. He just seems, luck just happens to my father-in-law. But on a roulette wheel, they have a board next to it, like an electronic board that shows you what the previous rolls have been or spins have been. So you can look at the board and see, I don't know how many's on the board, but the last 6 spins or 10 spins or something like that, you can see what they've previously been. So my father-in-law passes the roulette wheel. He looks to see if the 0 or the 00 has actually come up in the recent history of the board. Okay? And if it hasn't, he'll bet on the 0 and the double 0, which is very interesting, right? Because each spin is what we remember calling independent, right? No effect on any other spin. The fact that it hasn't come up in the last number of spins has absolutely nothing to do with whether it will or it won't on the next spin. This is how he plays this game. So he bets on both numbers. He puts money on both of them. If he bets one chip on each number and a chip is worth $10, what is the expected value of his bet? Okay, so we're going to look at how we process an expected value. Sometimes when you have an expected value, there's more than one outcome. So, sorry, that just should have said E. I don't know why I continued there. So you might if you roll, an even, you get like $5. And if you roll a prime number, you get like $2. And if you roll an odd, then there can be multiple outcomes, right? But in this scenario, there's really only two outcomes. It either lands on your number and you get money back, or it doesn't. Does that make sense? There's no in-between ground where you get some of it back and not the rest. It doesn't happen that way. So there's really only two outcomes, winning and losing. Okay? So each time, this A sub n business over here, they represent the outcome. So these are the outcomes, and we only have two outcomes. And these are the probabilities of that outcome. So you'll always have the same number of probabilities as you do outcomes. So on ours, we really only have the outcome, or the value, if you will, of winning. The value if we win times the probability that we win, plus the value if we lose. Whoops, I should have put that like this. Value that we lose times the probability that we will lose. Okay, so let's actually talk about the losing first, because it's easier to do than the winning one. What happens if the number lands on a 7 or a 12 or a 22? Well, we lose. How much do we lose? $20. Why is it 20, Asia?
Because he bet on two numbers.
Right, he put money on two numbers. So he put $20 into the pot. He's going to lose all $20. So this is a negative 20. What's the probability that he's going to lose?
36 out of 38.
Right, 36 out of 38. Right? There's a 36 out of 38 chance he's going to lose, because he bet on two numbers and neither of those show up. So what's the value that he gets if he's going to win? This is the hard part on this particular one.
Is it still the same, like you earn 35 chips with the same number?
Mhm. So he's going to earn 35 chips.
And chips were $10.
And the chips for $10 a piece, 350. But,
Then he has one and he gets it back, so right?
so does it say he gets the one back? He gets the one back. So he gets 35 at 350. So he gets his one back. So that's a wash, right? Like nothing happened with that 350, right? He put it in, he got it back. But he still lost the chip. Like if it lands on 0, he loses his chip that he played on the double 0, right? Are you guys with me? So he's gonna get 35 chips. There's one right here that doesn't count because he played it, he put it on the board and they just gave it back to him. So he didn't lose it and he didn't gain it. It just changed position. So it doesn't count. And then he loses one chip, the chip that was not actually on the right number. Can you picture it happening? Okay, so this one just, it changed locations. It was played and it was given back. This one was taken because it was on the wrong number. And then this was the payout. So the grand total that he actually has is 34 chips. New, like in his pocket now, that he didn't have before. And that would represent how much dollars? 340, right? How much dollars is terrible English, but we're going to go with it. 340. What's the probability that he wins?
2 out of 2.
Yeah, it's the one we talked about on this screen, right? 2 out of 38. 2 out of 38 is the chance he wins. When he wins, he actually increases the amount in his pocketbook, basically, by $340. All right. So if you don't have a calculator out yet, go ahead and grab one. So these numbers are kind of atrocious because we're dividing by 38. But we have our 340 times 2 over 38. And then we have our negative 20 times 36 over 38. It's really important as you're looking at this problem and thinking about these problems too to make sure you get the signs in there, right? The value of the loss needs to be a negative. He's lost money. The value of the win needs to be a positive. He's gained money. And what did we get when we calculated it? Remember, this is an amount of money. Did anybody get a calculation yet? What'd you get, Aisha? It is negative. That's okay.
-122,400.
I think you got a typo.
61.
Oh,
Yeah.
is it in a fraction form?
Yeah, I changed.
Turn it into a decimal. We want decimals because we're
Oh,
dealing with
okay,
money.
gotcha.
Decimals for money.
-339.058.
That sounds too big. Yeah, that's what it should be. But let me see if I can figure out what's going on in the calculator. This is times. You don't want times here.
Okay.
Let me pull it back up and we can change the sign. You can just put a plus sign in between them and that'll work. There's the same
Okay,
answer.
perfect.
Cool. All right, everybody else who was able to, did you get a negative 1.05? Okay. So over time, if he does this enough, the average value of a single play is that he loses $1.05. That's what happened here, right? Now, that's not really what happens. He either loses or he wins. But this is the average, the expected value over many, many, many times of doing the same thing over again. Which is why the casino will win, because the outcome to the player is a negative $1. And the winnings then to the casino is $1. So on average, they expect if 15,000 people came through there, they're going to make about $15,000. Does that make sense? Sometimes they make money, sometimes they lose money, but on average, they make about $1 per customer. Are you familiar with Deal or No Deal? You guys seen that show? Okay, so if you're not familiar with it, what happens in Deal or No Deal, it's fun to watch, by the way. It's totally a random guessing kind of thing. But there's like cases of money on the screen, and there's people that hold the cases of money, and the person chooses their case, and that's their case, and it sits right beside them. And then they eliminate other cases, and they show them one at a time about how much money they're not going to get in the cases because they didn't choose that case. So in the television show Deal or No Deal, they're down to 2 cases. So they've got the case that they chose, and they've got one case up there. And they're given the opportunity of either keeping their case, swapping their case, or taking a deal that the banking broker, is offering them. So obviously there's got to be some sort of rhyme or reason to what value they give to the deal. It needs to be enticing enough that the person thinks, ooh, do I want to do that? But maybe not quite so enticing enough that it leaves you wondering, will they or will they not, right? That's the way the game goes. So the cases are down to $250,000 and $10. If you're the banker and you want to give a reasonable offer to the contestant, but not too lucrative, right, not too much, what deal would you offer and why? Well, you'd offer the deal based on expected values, right? What's the expected value that their case has compared to the case that they don't have? And so there's 2 outcomes in this one, and both of them are wins. Nobody's losing any money in this particular one, right? They either win $250,000 or they win $10. And at this point, what is the probability of each case? It's 50-50, right? It's a 1/2 probability, 0.5. Like so. So if we multiply, add, and so forth, this actually ends up giving us the average on this one because there's only 2 cases left. $125,005. Now, that doesn't exactly answer the question because the banker could give kind of a range of values that would still be appropriate to this question, right? So when we answer this question, we're going to be a little bit more vague than just saying he should offer $125,005. That's not real. I mean, that's not the way it would be sort of thinking through this. So it'd be something like this. You'd offer around $125,000, wouldn't you? Yeah, it'd be offering around $125,000. Slightly more would be, better for the contestant. Slightly less, better for the bank. Yeah, they do have Deal or No Deal at the arcades. Chuck E. Cheese even has it, by the way. Yeah. Any questions on that one? Now, we still can't really talk about the game being fair because in this game, there is no fair because it's never going to equal zero, right? The probability, I mean, this expected value is never going to be zero because they're going to win something. So this game is never fair. You could talk about what seems to be a reasonable offer, a fair offer, but we aren't meaning the same thing by the word fair as we are when we talk about a fair game. I mentioned that because we're going to talk about fair games on the next one. We're going to look at a lottery. In a given lottery, we know that the odds of winning, hopefully you've seen the first half of this video about odds because we're going to need it. Odds of winning the lottery are 55 million to 1. Good luck. What is the probability? Remember, odds and probability are not the same thing. So the odds of winning the lottery are 55 million to 1. So what would be the probability of winning the lottery? Close.
154,999,900.
So you're thinking along the right lines, Braden, but it's not subtraction of 1, it's addition of 1. So it's 55 million and 1. Okay? So 1 and 55 million mean one person wins, 55 million people lose. So that means that the total number of people who played is 55 million 1. Does that make sense? That's how odds and probability are connected. Okay. If the grand prize is $14 million and a ticket costs $5, is the game fair? So fair games have to do with whether the expected value is 0. Now, it shouldn't be fair. Again, otherwise, right, like, what's the point in having the game in terms of, like, somebody running it and paying their employees and so forth, right? Like, that's not how it's going to work out. So we're going to examine that by doing the expected value. So again, we have either the winning or losing. So I'm going to abbreviate it the same way that we kind of did before, maybe a little bit more abbreviated. But it says that you could win. You could win $14 million. So if you win $14 million, what do you actually win?
Whatever it is minus 5.
Yeah, minus 5. 13,999,995. Because it cost you $5 to play. And what's the probability that you won?
The 1 over.
Yeah, part A, or the beginning part, right? Yeah, the part A, it was part A. 55 million, 1. Okay, so what's the losing value? What do you lose? $5. And it is a loss, so we are using a negative 5 to represent that we are down $5 in our pocketbook. And what's the probability that you lose?
55 million.
55 million over what? 55 million one. Are you with me? It is ugly. It's really ugly, and your calculator will be able to handle it just fine, but you want to be careful putting it in that you don't miss a zero or something like that because it's easy to do. So if we put these into our calculator, you guys check it for me. What do you get? I will spoil the fun and tell you it's negative. No way. I know, no way it's negative.
Negative like 4.7.
Can you give me two decimals since we're dealing with money?
Negative 4.75.
Yep, that's right. So it's not fair, right? I mean, so this does not equal 0. So it's not fair. If a question asks you if something's fair, it means to show mathematically, is it fair or is it not? That's what we did here. No, it's not a fair game. So state lotteries are funny. They always want to say they're benefiting something, and it's usually education. So if the grand prize, with these state lotteries, the proceeds are said to benefit education many times. Under these conditions, if all proceeds did benefit education and 1 million tickets were sold, what is the expected value? Well, each ticket is expected to be a negative 475 to the consumer, the person who bought it, which means it's a positive 475 to the people running the lottery. Does that make sense? So I have 475 from the ticket that's considered sort of the profit to the lottery. And there's supposed to be a million sold according to this particular part. So what would you actually be earning for education? $4.75 times a million.
Just 475 million.
You're close. It would be if it were 475 times it. But
750,000.
right, 4,750,000. 4,750,000. This is sort of, if you ran this lottery over and over and over and over and over again a bunch of times, the expected value of running the lottery each time, selling 1 million tickets, would be $4.75 million, that sort of thing. But on an individual run of the lottery, one point in time, right, it doesn't work that way. It's kind of like asking, what's the probability of having 6 boys? Well, it's not real high, but what's the probability of having 6th boy when you've already had 5 boys? 50-50. Right? The individual single outcome is different than the culmination of everything over time. So there really are only 2 possible outcomes. One outcome is that someone wins. Actually, we'll do the no one wins first because it's shorter. My space will work out better. No one wins. So if no one wins, then everybody's actually paid $5 a ticket, right, for the 1 million tickets, which would mean that we end up with $5 million, right? $5 million is what's happening if nobody wins. That's what really happens. Nobody wins, state gets $5 million. The other possibility is that someone wins. Now, the reality is, too, that they still had $5 million paid, correct? So $5 million is what comes in. This is what's paid. But what's the payout? What do you get if you win? 14 million. Does anybody see a problem? Ooh, if somebody really wins, we just dipped into the education fund and we gave it to somebody. You are now at negative $9 million. And this is one of the reasons why it is kind of a matter of conscience when you think about these things. because there's really no good outcome. One outcome is nobody wins, which means, yay, the state gets to take away everybody's money who was foolish enough to play. So you're rooting against all the people who are supporting education, not wanting them to win. Or you're supporting the people who are wanting to play, yay, 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 but then if they win, your education fund that you were supposed to be building up is actually depleted instead. Kind of a problem, right? Yeah. Yes.
Sorry to be technical, but in a way, you'd be probably paying a lot of taxes off of that, and then that's going
Yeah,
to...
so what ends up really happening when somebody wins a lottery, generally speaking, is that they have a payout that they can't get all at once. It's paid over time. So they can either get 50% or something like that of the payout money. So like if this were 14 million, they might be able to take the 7 million now and then they're done, like a one lump sum payment, or they can get paid $14 million out over like 20 years. That's how they run those things, actually. Yeah.